Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving here today, as it is every day here in my virtual classroom. Stepping aside as we jump into the section 3.1 to 3.3 quiz review in the Big Ideas Math Integrated Math 1 textbook. This is on things starting with functions. We're graphing linear functions as a whole in this chapter. We're going to get really into the big parts of graphing functions in the latter half of the chapter. But we began with a lot of definitions, comparisons, understanding and describing when things are and what's linear versus nonlinear, what's a function versus not a function with relations. We need to know about domain and range, independent and dependent variables, function notation's a big part of this, discrete versus continuous, a lot of things like that, and they're going to be represented within the 16 questions that we have in this quiz review. So if you'd like to download this PDF, jump to the description section down below. You can find this. If we have to do any graphs, which I'm going to guess we're going to have to, you can also download graph paper below, or of course use your own graph paper. It's up to you. But if I go off of scale or certain things like that, you might want to follow along with mine just in case. Use a ruler, of course, because we're doing things with linear functions, but we don't always connect lines either in case we have something discrete. Just keep that in mind. We'll talk about it when we get there. Without further ado, I'm going to go ahead and get started. We are starting with problem number 1 and then number 2, two different representations, a table versus set of ordered pairs. Determine whether the relation is a function and explain. What we're looking for here is we have different inputs versus our outputs, and our inputs are -1, 0, 1, 2, and 3. Now, I see no repeats of these x values, which is really one of the key things I need to look for when we have a table or when we have a list of ordered pairs here. No x's repeat. And if no x's repeat, then that probably means it's a function, because I would need to have a repeated x value, let's say -1, if this were a -1. If these are both -1s, then I'd have different y values for the same x value, which is something a function is not allowed to have. That's its very definition. So this one actually is a function on number 1 because every input has exactly one output. That's what we're looking for. Every input has exactly one output. Now on number 2, and I didn't really look at it yet, but on number 2 I have a list of ordered pairs. Those are x's written first and y's written second. Look at the x's more importantly first. -10, -8, -6, -8, -10. Okay, I happen to see repeats with two different values, both -10 and -8. Now I'll let you know that we only need one instance of non-functionality for it to not be a function. But given the -10 input has an output of 2, and the -10 input has an output of 6, that is no good. That's a no-go. That's what would make this not a function. Of course, we can check with -8 as well. -8, 3 and -8, 8, two different y's for the same x. Once again, not a function. So two different sets of inputs have, there are two different sets of inputs that have more than one output, which is an issue, basically. And those are the representations, whether it is, again, an ordered pair, or whether a list of ordered pairs, or whether it is a table that when you see that you say no good. Now I want to say a few more things on that before we move forward, because we might not be able to talk about that again afterward. So not a function. Both the inputs, -10 and -8, have more than one output. Even if it happens once, it's an issue, right? Even if it happens once. Now, going back to number 1, you can notice there's a repeat on the y values of 4 and 4. Whether I input 1 or 2, I get an output of 4. That's allowed. For function's sake, that's allowed. Two different inputs can have the same output. Okay, that's one thing. The next thing is, don't just say just because a number repeats that it makes it not a function, because I could put another 2 and 4 right here on number 1. 2 and 4, but this was 2 and 4 as well. So as long as this input gives me the same output, doesn't matter how many times I repeat it, that would also still be a function. Now it's only tables and ordered pairs for which we actually make these determinations based on repeats. There are also things called mapping diagrams, and based on this thing, I don't see it here. Honestly, guys, mapping diagrams are not a big part of what we do beyond this stuff right here. They'll be a part of it, but it's not even a part of this quiz review. And I don't know if you're quizzed on it. You can take a look at some of the mapping diagrams we did in section 3.1. But mapping diagrams won't repeat numbers because they only show domain and range values, which don't repeat themselves. But they'll show an arrow split, for example. And on graphs, the kind of repeat you'll do is through what's called a vertical line test. And I don't know if we're doing vertical line tests on here either. It doesn't really look like we are. So there are a couple things, guys, that are not being represented on here. I'm not saying like, this quiz is a problem. No, I'm saying they only have a select few of them. And if you'd like to see more, definitely go to section 3.1 and explore that morezies, because there are a lot of other things in section 3.1 they have to talk about, and we're going to move forward to them. So numbers 3, 4, and 5, they say find the domain and range of the function represented by the graph. Now, the graph has points on them, whether they're represented discretely, like these, or continuously, like these ones. So on number 3, we have a set of discrete values. Now, they never defined the word discrete in this particular section, and for the life of me, I don't know why, because we really do need to talk about how functions or relations are discrete versus continuous, meaning we have a broken up set of points. They are finite, they are specific. We can write them as a list, and that's what we're going to do when it comes to domain. So the very specific points here are like 0, -5, 1, -3, things like that. Domain is in reference to the x values. What x values exist on this graph? When x is 0, there's a point that exists. When x equals 1, there is. X equals 2, there is. And 3 and 4. There's no value when x equals 5. There's no value when x equals 1.4. Nothing like that. So only the numbers 0, 1, 2, 3, and 4 exist on these x values on the graph. Those are your domain values. So on number 3, when I list my domain, I can say it as, and I'm going to type it, I can say it as 0, 1, 2, 3, and 4. If you heard me about mapping diagrams, which we're not doing, I stated mapping diagrams list domains and ranges within them. And I stated that domains and ranges do not repeat themselves. So be aware about that. Even though there was nothing to repeat here for domain, let's talk about range now and see what goes on. Range, the very smallest value I see, remember I said this point is 0, -5. Range has to do with y values. So -5 exists in your range. What y values exist? -5 exists. There's 1, -3, and there's 4, -3. So -3 exists, but this is where I'm stating that you do not repeat values. -3 just needs to be listed once. Does -3 exist in your range? Yes. Okay, move on. Don't say -3 and -3 again. So -5 exists, -3 exists, -1 exists, and +1 exists. So these are the 4 y values that exist as points in your function. So for as far as range goes, and the other part I do for domain and range is I list in increasing order. So -5, then -3, then -1, and 1. We're not attempting to pair up our domain elements with range elements when we're listing them. That's actually what mapping diagrams are for, where we say, hey, 0 goes to this number, to -5, and things like that. That's not what is happening here. Now, I wrote them as a list because it was a discrete relation. They are separate that way. Let's move to number 4, where we do not have a discrete relation. We have a continuous relation. Not just because the arrows, just because this right here, there's no disconnect between your values. It's just a constant flow of values. Is there a point when x equals 0? Yes, it's right here at y equals 3. Is there a point when x equals 1? Yes, it's right here. And I can plot these points and make a graph. If I knew the equation, I could use a table, blah, 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 and I connect the dots. But connecting the dots is because every point exists between 0 and 1 and 2, and later in x equals 3. And that's the next idea with this arrow set. This keeps going down and right, down and left, keeps going forever, and those are indicators in our domain. Now, one of the things about domain and range, because it's continuous, is we do not write this as a list anymore because it's not just specific integer values. For domain, it's every value. There's no x value this doesn't hit. You can tell just between -2 and 2 alone, here's x equals -2 and x equals +2. Between -2 and 2 alone, we see a point hit everywhere on there. When x equals 1, like I said, things like that. And even the decimals. But even beyond that, when x equals 3, there's a point down there. When x equals 4, there's a point somewhere down there. You can't see it. It's out of the window range. But even when x equals 100, there's a point that's way, way, way down there. There is no value of x which does not exist here. Therefore, our domain for this set is all real numbers. All real numbers. That's what we'll say for this one. Now, there is a symbol that I use for all real numbers, and if we have to use it later, I will be pointing to it, and it looks like this. It's not my symbol, but it's my version of how you write the symbol. Let me try that again. It's kind of like a capital R, but it's like a double blocked capital R like that. You can look it up. It looks a little fancier, but that's the version that I use for that. And it's important because range does use a capital R literally, and I want to make sure you don't confuse it with range. Now, range has a different thing going on because it's not all real numbers. It goes down forever, And I think most people understand it goes down forever, but understand it does go right and left. Just because it goes steeper downward doesn't mean it ever ends up going vertical. But it doesn't go up forever, right? That top value when x was 0, y was 3. 3 was that maximum y value that it hit. It doesn't go beyond 3. There's no y value beyond it. So the highest point is 3. It goes down forever from there. We can represent this, instead of a list, of course, we can represent this as an inequality. What y values exist on our graph? Every y value that is 3 or less than, right? It's at most 3. Y is less than or equal to 3. And that's how continuous functions roll, man, or relations. That's how continuous things roll with respect to domain and range. We use inequalities, or in some cases, all real numbers. Now, number 5, I'll play more in the scanner role with this. I'm going to draw myself a vertical line right now and let this scan left to right. And let's see how far left this graph goes, how far right this graph goes. When my sensor goes off is when we hit points. Ready? Here we go. Beep. Okay, when did my sensor start? Beep. 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 Right? -3, when x is -3. Sorry if that was annoying. When x is -3, we start hitting values. We don't stop hitting values up until x equals what? +3. From -3 to +3, x values exist. Now, we can write an inequality set for this as well, but it will be a compound inequality. Let me copy and paste this little guy because I'm going to use it again. So for domain, our x values will be everything between -3 and 3. Now, because of last chapter, we should really be comfortable with how to write that. Between -3 and 3 will look like that for our domain. Our range would use more of a horizontal line sensor, and it would look like this. And we start letting the sensor go off when we start seeing values hit. So here we go. Beep. Now notice that just because I went past this point right here, you might be looking at this and saying, wait, why is your sensor still going off? Why is it going off? You're not hitting any points there. Look to your left. Look to the left. There are more points being hit there. Remember, y values, when we listed, remember when we said -3 existed both here and here? It doesn't matter as long as you list it once. That's all that matters. And I'll say, is there a y value of 2 somewhere? You say, yeah, there's one right there. Look at that. Is there a y value of 2.5 somewhere? No. Yes, there is. Right there. And by the way, there's a y value of 2 over here as well. Y values can repeat themselves. They repeat themselves infinitely right here at x equals -1. Any number between 0 and 1 for x is a value for y. And remember, that's an infinite set between there. So the point is, y values can repeat themselves, but they only need to hit once. The question is, what y values exist? Is there a y value that exists at 3? Yes, it's up here. It doesn't exist up here. It doesn't matter. It doesn't matter as long as it exists. So my sensor goes off once again. Beep. All the way from -1 up to 3. From -1 up to 3. So as far as this goes, the range, y goes from -1 to 3 on y. Like so. Now, my general idea is I don't want to go slowly through that for, other domain and range problems in the future, even for chapter review. I'll probably make sure that whatever review things they have for examples, I'll just talk through those and make it happen. But as far as quiz review, for some reason, domain and range is a hard topic for people to really grasp. That's why I really wanted to slow this one down and see if I fully covered that in that way. If so, awesome. Because we can answer those significantly faster as a result once we learn it. Okay. Determine whether the graph, table, or equation represents a linear or nonlinear function. Explain. Now, it appears that it is going to be a function. They're saying, all right, all of these are cars. Tell me which ones are sedans, coupes, and pickups, and SUVs and things like that. So they're all functions. We're not testing that. Are they linear versus nonlinear? Now, this number 6 is a graph that's a line. It's a line. If it's a line, then it's linear. Now, as we go back to numbers 4 and 5, these are nonlinear. I want to make sure that we can stress that, right? These were nonlinear. This is linear. So number 6, it looks like I can type out the rest of what I'm going to do here. But number 6 is linear. They say explain because the graph's a line. That's all. And you see examples of nonlinear in 4 and 5. Now, that's just for graphs, right? We have that luxury of having that for a graph. Number 7, we don't have the graph, and I'd prefer not to sketch the graph to determine that. We have to go by something else if we can. And so for number 7, I'm going to copy and paste that one over. What we're looking for is whether or not there's a constant rate of change from one x value to the next and also from one y value to the next. So when we look at this table, the x's increase from -5 to 0 and from 0 to 5, they're increasing by 5s. So as we have a constant rate of change on x, which is kind of the expected part, the question is on y, are we increasing by a constant difference? From 3 to 7 is an addition of 4, 7 to 10 is an addition of 3. Those are different because it is not a constant rate of change as x increases constantly. This is non-linear. It's a function. It's a function, but it's non-linear. Y does not increase at a constant rate as x does, as noted by my values. Now, they don't need to actually increase. Y could decrease at a constant rate and still be linear. Okay, but just not the case here. Now, number 8 is an equation, and our basic understanding here, and again, we're going to get into it deeper, especially in section 3.5, but we started to adapt this form y equals mx plus b. I'm going to write it above right here. Y equals mx plus b. And this is the ideal form that we're going to be doing a lot of graphs out of. Not all graphs, but we get to do a lot of because we get to input values for x right here, do some computation with it, and get values out for y. Now, there are a lot of other equations where y can equal something with x's in it, such as this one. But this, all linear equations can be expressed in this way. Now, m and b, you're like, what's m and b? M and b can just be any number, literally any number. They can be 1, they can be 5, they can be -4.2, they can be 0. And when there's 0, 0 times something means it actually goes away. So sometimes you won't even see the x variable there. Or sometimes you won't see the b variable there if it's 0. Or it can be the square root of 7. But x and y specifically need to be raised to the first power. They cannot be a product of each other. They cannot be multiplied. They cannot be in their own exponents. They cannot be to the x power or something like that. They can't be inside radicals. They can't be in their denominators. So things like that need to exist for x, and y needs to exist. Purely y needs to exist for a linear function. Notice we mentioned these are functions because x equals equations are actually vertical lines. And I don't know if we get to talk about the vertical line test here, but a vertical line would fail the vertical line test. A vertical line says you have multiple y values for the same x. So anyway, in this case here, the question is, can I rewrite this equation in y equals mx plus b form? Well, y is by itself. If I distribute x into both of these terms here in the quantity, x times 2 is 2x. Okay, y equals mx plus b, x times -x, x minus x. No, it's x times -x. That's actually -x squared. -x squared, that's not the same thing as a b. B needs to be a constant value here, not a constant. So this is not y equals mx plus b form. I can't get it into y equals mx plus b form. This is not a linear function. This is actually called a quadratic function. You see this graph number 4? This is what this equation would look more like. Exactly? No. But like this? Yes. This equation would look like that. We know that graph's not a linear function. This is not linear because of what I pointed out above. That b is not a constant. It's not written in this form. I couldn't get it in that form. Now, are you required to get it in that form to express linearity, or at least to judge for yourself whether it's linear? No. Is that a way to indicate when it says explain or show that? I would recommend it, and it's a further practice that we'll be doing anyway. So maybe it's something you try and do. But that one's a no-go. All right, numbers 9 and 10, determine whether the domain is discrete or continuous, explain. Now, I already made a statement about this when it came to graphs. We said this was discrete versus these were continuous here, right? But those were on graphs. These are not graphs, and even if we plotted these points, which are a little out of reach from what I'd want to do, even if I plotted the points, the question is, should I connect them or not? Now, this is all based on context. Discrete, as you can tell, has points that are separated, basically no real fractional values or microcosms of whatever individual thing we're talking about. Hopefully one is continuous and one is discrete so we can really make that distinction. But on number 9, we have depth in feet and pressure in atmospherics, I believe is the name of the unit. So there's probably water depth. Well, actually, no. Actually, maybe depth in air. Actually, I don't know. I don't know if that's water depth or air depth, whatever. But as you start to go in some okay, let's say it's water. I don't know if atmospherics work in water like that. Now I kind of feel stupid. Sorry about that. But, or air. But as you go more underwater, let's just say for argument's sake it is that. As you go more underwater, the amount of atmospherics, the amount of pressure increases. Okay, you get your barometer out and you figure out, oh, I'm underwater. I have atmospherics apparently, or maybe not, whatever. It's broken underwater. Now, do they have to be at specific intervals? Is it just at every foot, at every 33 feet or something like that, that it must just go up by 2, that there's no value between 2 and 3 that it hits, that it must click at that point? Or can I progressively decrease more? Can I go to 34 feet, 35 feet, 35.1 feet, 35.0001 feet, and the atmospherics change by decimal fractional amounts each time? I think the latter makes a lot more sense in that situation, because of that nature of what we're doing on that problem. The depth can be any number of feet for this set. Whether water or whatever, this is a continuous relation. Now, if I knew my science much better and knew whether this could be in air versus underwater, because when I hear the word depth, I'm thinking underwater. When I hear atmospherics, I'm thinking of air. But whether I could be one or the other, you could probably even have some negative numbers. If positive was above ground, above surface, above water, and negative was below water, you could probably just do both. I don't know if you could have negative atmospherics. We never said whether it's linear or not, but that's a continuous set. Number 10. Number 10 says hats and cost in dollars. I buy 2 hats, I'm going to spend $36. 3 hats, $54. 4 hats, $72. First of all, it looks linear, but that's not the question. Is it continuous or discrete? Could I buy a fraction of a hat? It's not argued whether you could take a thing and slice a hat in 2. It's, will they allow you to? Will they chop the price in half? Things like that. No, this is one of those things where with discrete, you kind of say the phrase like this: either you buy the hat or you don't, is kind of the way that we talk about those. There's no kind of fractional version of it that you pay on cents on the dollar or half of $18 and things like that for the hat. Either you buy the hat or you don't. This is an example of something that's discrete. You plot that one point and you don't connect them because there's nothing between the two for flow. So discrete, because the hats, because they're speaking specifically about domain, by the way, even though they should really be domain and range, the whole relation. So discrete hats can be sold in whole numbers only, by whole amounts only. It's kind of a weird sentence, but they asked us to explain. And there it is. Okay. Number 11, for W of X. Okay, this is section 3.3. This is function notation. We're probably more used to seeing f of x. Actually, you don't get the luxury of seeing f of x anywhere on here. So you're like, hey, y equals f of x. Okay, I'm actually learning that. I'm learning y equals f of x. W of x, what the heck is that? It's just another function. This says to us, I just wrote y because I was going to say the letter y. This says to us, y equals negative 2x plus 7. That's all it means. We're saying out loud w of x. No, that's not w times x. That says w of x. W is a function of x. And it's the same thing as y equals. Keep that in mind for any function notation that we do. It says find the value of x for which w of x equals negative 3. Do you know what else that means? Find the value of x for which y equals negative 3. So what can we do? We can substitute negative 3 in for y right there. But of course, there is no y here. They didn't write one. They said w of x equals negative 3. No matter. This could say booger equals negative 2x plus 7. Find the value of x for which booger equals negative 3. It doesn't matter what it says. We're replacing booger with negative 3. We're replacing w of x with negative 3. Like we'd replace y with negative 3. We're still trying to solve for x for the scenario. For what input gives us this output? That's the question. This is a simple algebraic solving. This is something we've been doing since chapter 1, so I'm going to go pretty quickly on this portion. Negative 2x equals negative 10, and we divide by negative 2. Signs change. We get x equals 5. When I input 5 into my equation, I get negative 3 out. As a double check, we're probably going to do this in the next set of... Oh, no. Well, not really. It says graph the linear function. So as a double check, I'm going to substitute 5 in for x. So this is what we do when we say find w of 5. Apparently w of 5 should be negative 3. Let's see. We're going to substitute negative 5 in for x here. Negative 2 times 5 is negative 10, and negative 10 plus 7 is 7 minus 10, which is negative 3. There's a good old double check that it worked out the way we were supposed to have it work out. So that's all that means. This is what function notation looks like. This is specifically how we'd write it a little more so often. When it says find w of 5, it says input 5 into your equation, give me the output. W5 equals negative 3 means when x is 5, y is negative 3. Numbers 12, 13, and 14 say graph the linear function. So in order to graph this function, what we've learned so far in this set is we input x values, we get out y values. So just like what I just did for that input of 5 and got -3 out as a double check, we could do the same thing on these ones. For this first problem, I am going to generate a full table and use full function notation. After that, I'm going to reduce it probably to smaller, bits. You'll see what I mean. But for x and y, I don't know how to separate this yet. Let's see. X, y. Let's try that again. I'm going to plug in the values -2 to 2. It's a common practice to try some negatives, some positives, and 0 as long as we feel that, I wrote g of x plus 3. That is not an equation. G of x equals x plus 3. Okay. So from -2 to 2, I can substitute these values, get some y values out, and we'll plot them. Now, like I stated, I'm going to be showing you the inputs here. G of -2 means we do -2 plus 3. And that's 1. Therefore, the y value is 1 and x is -2. G of -1 is -1 plus 3, which is 2. So we get 2 out from there. G of 0 is 0 plus 3, which is 3. You'll get used to the fact that when x is 0, y is just going to be the constant value because the x term goes away even if it multiplies by something. So it's just 3 in that case. And at some point, again, you're going to start connecting and making, a pattern recognition of what happens. Can you guess what this will be without actually calculating it just by seeing the pattern of y's? I'd assume so. By the way, I'm going to turn this y into g of x. I can say y out loud and it means g of x. G of 1 is 1 plus 3, which is 4. And g of 2 is 2 plus 3, which is 5. Very basic equation as a whole, right? Simple calculations, and we're going to graph this as well. So I'm going to duplicate this down below because I got to do this graph. Again, if you'd like to download one of the graphs that I have as PDF or graph paper sets, you can. I need to take and copy mine and paste it. No, hold on, it didn't copy. Give me 1 second. It's on the sidebar. You can't see it. I have it on every page of mine. There it is. Okay. Just in case we ever have to use it. So, these are the points that I plot. Now, why did I choose these values? Because I could. Because they would stay within my window range, things like that, or at least I anticipate they would. Now, when we start doing future graphs, I'm going to say plot as many points as you can fit. This can't be all of them I can fit, but we are going to connect these points with a line. So, the other part about this on its state is, why did I choose these points? I mean, literally, when I said because I could, it's because they fit in our domain. These domains, there's no reason that any of these linear functions don't have an all real number domain. You can plug in anything, left, right, center, -100, +100. If you could fit them in this window range, go ahead and do that. This is where we use a ruler and connect this line like this. But honestly, I'd like to extend the line as far out as I could just to extrapolate what would happen if I plugged in deeper x values, positive and negative. Like if I substituted maybe 7 for x, what was it? 7 plus 3, I'd get 10. Does this go to 7, 10? Yeah. So if I use a ruler, then I can get that going exactly like that. These are the 5 points I plotted, but that's still the graph with it. Let's go to number 13. Let's do the same thing on that one. We have p of x equals -3x minus 1. Now I'm going to do the same table thing, x, y. I'm going to substitute everything from -2 to 2. Some negative, some positive, and 0 is a good way to go about this. However, this time I'm not going to write function notation leading into it. Let's try a mental version of it, shall we? Now I'm going to start with positive if it makes it easier for you. -3 times 0 is 0. Minus 1 is -1. It's p of x, by the way. -3 times 1 is -3. Minus 1 is -4. -3 times 2 is -6. Minus 1 is -7. So that's what we're doing, right? We're substituting these values for x, getting them for y. -3 times -1 is +3. Minus 1 is 2. And -3 times -2 is 6. 6 minus 1 is 5. Now you might also notice this pattern of subtracting 3 each time, which is something that a linear function should do, right? Constant change, rate of change in y as constant rate of change in x. So this graph, we can plot these points as well. They're a little bit steeper than last time, even though the x's are pretty tight still. The y's are a little more separate. -2, 5. -1, 2. 0, -1. 1, -4. And 2, -7. Ha 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 ha. Hiya. Okay. Oh, by the way, I don't know if I mentioned this, arrows, right? By default, my line already has arrows, but arrows, all real number domain. All real number domain. It continues left and right. Therefore, it continues up and down, and we have to indicate that. There's the graph. Okay, number 14. Has m of x equals 2/3 x. Now, I want to stress that all three of these equations actually take on that form y equals mx plus b. If you can keep in mind function notation, m of x, p of x, g of x, m of x, and p of x all mean y. However, this is all mx plus b. A number could be multiplying by x, such as 1 and -3, and in this case 2/3. Those are your m values in this case. B, the b values here have been 3, -1, and in this case here, a 0. So these are all y equals mx plus b form, which means they're linear equations in their own right. And these are the different takes that we're going to be having on y equals mx plus b form. We're going to learn to graph those in shorter order than tables coming up. I think, like I said, in section 3.5. Now, for x, y values here as I make a table, I would prefer this time to not just go from -2 to 2. This time, I would prefer to choose x values that I can divide by 3 with. Now, 0 is a number I can still divide by 3 with. And negative numbers I can still divide by 3 sometimes, right? What can I divide 3 with? Multiples of 3, like 3 and 6. I'd love to plug in those values. I'd love to get values that help me more, not less. And I think the y values will also correspond in such a way that they'll fit on the graph. See, if I substituted 6 for x in the previous equation, I'd be getting -19 as a y value. That won't fit on my graph, so that was not worth it. But 2/3 of 6 I should be able to fit on here. That means -3 and -6 should also go here. Let's try them out. 2/3 of 0 is 0. 2/3 of 3 is 2. 2/3 of 6 is 4. Now, if you didn't know those off the bat, you're taking your number, dividing by 3. 3 divided by 3 is 1 times 2 is 2. 6 divided by 3 is 2 times 2 is 4. The opposite of those will give you -2 and -4. I'm not going to beat around the bush. There they are. And it seems to be increasing by 2 each time, which is, linear. So when we draw this graph, we get to go x as far as -6 to +6. And this is going to be a little more appreciated when it comes to connecting the dots because it seems like we've increased this a little further out. So this looks like this here. Like that. Now when I sketch the line that goes through, boom, there's my linear function like that, right? So those points a little bit more spread out, kind of better. And you're going to learn to kind of like having fractions, maybe not for calculations. You are going to learn to like them when you do this form, probably even more than whole numbers. I know that sounds bizarre, but you actually might, and there's a big reason for that. All right, 2 more questions on here. Number 15 says the function m equals 30 minus 3r represents the amount m in dollars of money you have after renting r video games. So the way that I'm interpreting it, because it doesn't sound like they're having us actually interpret, the way I'm interpreting this is, here's my money. I start with $30, and it looks like I'm subtracting. Looks like I'm spending $3 for every video game that I rent, and r is the number of video games that I rent. That way, when r is 1, I subtract 1 multiple of 3. When r is 10, I subtract 10 multiples of 3, things like that. Identify the independent and dependent variables, and they often don't ask you to do more than just come up with the variable itself. I like to describe them more, but independent variable is r, and dependent variable is m. Now, r, again, represents the number of video games that I rent. I can freely choose how many video games that I rent, sort of, because there's a limit on how much money I can spend. But I can freely choose how many video games I rent, and based on, depending on the number of video games that I rent, this is how much money I will have left in my, that I have in my wallet, in my bank account, whatever. So m depends on r. The amount of money depends on how many games that I rent. That's what makes it independent versus dependent. That's part A. Part B says, find the domain and range of the function. Is the domain discrete or continuous? Explain. This is one of those things, and I stated it in the section at the time as well. This looks like section 3.2-ish, but I'd identify 3.1. I'd like to identify discrete versus continuous first, right? My domain or my range, whatever, is dependent on whether I'm writing a list or using a compound inequality. Can I rent fractional amounts of games? Can I have a half a rental or something like that? No, you cannot. So either you rent the game or you don't. That sounds like something that is discrete. And if it's discrete, then our list needs to be as numbers. So when they say find the domain and range, the domain, and I'm going to type these out, domain is the number of video games I could potentially rent. Now, you can rent, right? It's not up to how many you can rent, although that's a part of it. It's how many you could possibly rent, from the lowest to the highest and everything in between. Now, what's the smallest I could rent? I could rent 0, right? You don't have to rent a game. So I could rent no video games, or 1, or 2, etc. And this would continue till when? This is the kind of thing where maybe you have to do some of it mentally for this, but the thing that I want to do right here, just as a side note, is figure out when do I have 0 monies, right? That I need the amount that I rent, the amount that I spend based off rentals to stay greater than or equal to 0, or my amount of 0 monies needs to stay less than or equal to there. So I could add 3R to both sides, like this, and then divide both sides by 3. You probably understood this anyway, but R is less than or equal to 10. Now, this is not, we can't write this as an inequality itself, but the fact of the matter is, once I hit $0, that means I have rented 10 games. So 9 and then 10. My list ends there. This does not go on forever. It stops at 10. Again, maybe you recognize that already, which is fine. I'm just giving you another indicator of what we can do there. But because it's discrete and not continuous, we do not write it as an inequality between 0 and 10 continuously. It's discretely between 0 and 10. Now, range is based off domain, and this is something where, again, we could plug in values. I'm going to do this kind of more so mentally. When we're substituting 0 into there, that means that we haven't bought any games. That means the 30 is still there. 30 minus 0 is 30. Now, 30 minus 1 times 3, 3 times 1 is 27. Now, here's what I'm about to do. I'm writing in increasing order. 30 minus 3 times 2 is 24. And you can tell we're spending another $3 every video game. That's why sometimes interpreting it beforehand is better. So I'm going to write the list here, and I'm writing in increasing order, but they're decreasing by 3 all the way down to $0, right? So 0, 3, 6, 9, 12, 15, 18, and I ran out of room, so let's do that. So it's discrete. Here's my domain and range for this set. Is that all 10 of them? Or 11 of them, excuse me. Looks like it. So that's the domain and range there. Now, if I drew a mapping diagram, 0 pairs with 30, and 10 pairs with 0, etc. But this is just how I'm writing this list. Part C says graph the function using its domain. And when they say using its domain, that means we don't go beyond it, right? Based on the domain being discrete, we don't connect the points. Based on this having only positive numbers, we don't go into negative land, right? We're only plotting these ones. Now, I did not specifically state which points these were based on seeing domain and range, but hopefully you heard it. Now, the y values on my scale only go up to 10, so let's bring it up to 30, and this will actually be perfect because they can go by multiples of 3, and these go by multiples of 3. Now, I'm going to keep my x's going by multiples of 1, and my x is actually r, and my y is actually m. So this is 30, this is 15, but this is still 5 and 10, right? This is still 5 and 10. This stuff is irrelevant, not a part of our domain and range, no negative numbers to be found. So 0 game rentals, $30 left. 1 game rental, $27 left. Remember, these are going by 3s, down by 3s. So it kind of just goes like this. It's a neat connection where it goes from that top part down to this right part over here. And again, we do not connect the dots here. This is all that exists for this. All of these are situationally amount of video games I can rent and amount of money I'll have left. Not amount of money I spent, but amount of money I have left starting from $30. Last question is number 16. It says the function d of x equals 1375 minus 110x represents the distance in miles a high-speed train is from its destination after x hours. So this is also function notation, d of x. So kind of section 3.3, right? Oh, I need an x right there. Here it is. The distance in miles a high-speed train is from its destination. Now, if you wanted true y equals mx plus b form, then this term would be written first. Hold on. Then this term would be written first. And then this term would be written second. If anything, I'm reminding you that this term stays negative, this term stays positive. I don't know if this is better or worse from what we do. Just letting you know that that's the other form. Okay, so we know it's linear. How how far is the train from its destination after 8 hours? So if x is the number of hours, then we can determine what d of 8 is to figure out that ultimate result. This is probably easier to do the calculation from. I mean, it's an either or proposition here. This is 1375 minus 110 times 8. Now, to remind you, you're not doing anything on this side of the equation, guys. We're not solving for d. I mean, we sort of are, but this isn't d times 8. We're not going to divide both sides by 8 at the end. Nothing like that. No. This just stays as it is. It's what is the distance at the 8th hour, all that. And we're just evaluating on this side. We're doing 1375 minus 880, and that is a 5 and a 9 and a 4. Is it 495? Is that wrong? I think that's right. 495 miles. We're 495 miles from our destination. We started 1375 miles from our destination. Now we're here. Part B, how long does the train travel before reaching its destination? This is one of those instances. It's kind of like the last thing I did when it said, when would we run out of money on rentals? Now, I wrote the previous one as an inequality because I didn't know if we would skip past, like we had $2 left and then we spent another $3. Now we have negative money. I didn't want that there. This time we're trying to find out specifically for what value of x do we get a d of x that gets us 0. Which x value is that? So we're going to substitute 0 into our equation for this one. So 1375 minus 110 times x. If I add 110 to both sides and then divide both sides by 110, we will figure out what that x value is that gets us our destination. Hourage, our destination time. I don't think hourage is a word. I don't know that number. Hopefully it's a nice clean number, but 1375 divided by 110 is 12.5. So x equals 12.5, and because it's a word problem, we have some contextual units with this. That's hours. It'll take 12.5 hours on our train till we arrive at our destination. Now, what this problem is actually stating as a whole is that we began 1,375 miles away from our destination, and our train, it's a high-speed train, guys, it's traveling 110 miles per hour. Pretty fast, but it's still going to take 12.5 hours to get there. That's over a third of the way across the United States from, east to west, whatever, if you did that. All right, guys, that is the last question. And that'll do it for this one. This is Mr. Robinson. Thanks so much for watching. Listen, this was pretty robust, but there were some things that were missed, specifically on the domain range front. We didn't hit mapping diagrams. We didn't do vertical line tests. I'm trying to think what else there was that was in particular. We didn't see an f of x, but that doesn't really matter. There were some ones where we did interpreting function notation. I interpreted some of it for you here, but they didn't do a lot of it in this case. So there are things, if you want to look at them more, you can go ahead and do so in the actual individual sections. Find the playlist down below if you want to find different kinds of questions for your quiz review. But I wanted to go slowly through this one. I really feel like I did. I wanted to go slowly through this one and make sure all these really make sense, because what we hit next, we're going to do a lot more on graphing out of different forms, I believe. We have standard form next and then slope-intercept form next. So those two things might not feel exactly like these kinds of questions anymore. So I wanted to make sure that I hit these ones here. They're their own separate thing. The next part of the chapter is its own separate thing. So thank you guys so much. Take care. I'm going to see you in the next one.